So, welcome back. Yesterday, we discussed the topic of how to describe the probability of stochastic processes generated by the Langevin equation. So, we looked at two fundamental probabilities. The probability of generating an entire stochastic process, or if we want to keep the connection with physics alive at each step of a molecular trajectory where the label here basically corresponds to time steps. So basically it's the probability, well, you can say if you given the initial condition x naught, this is the probability that you start from x naught, you jump to x1, x2, then from x1 you jump to x2, to x3. Now I want to appreciate that what we call the molecular trajectory in this course, since this is a course for macromolecular systems after all, is nothing particularly molecular. It is anything generated by a stochastic process governed by the equation xk plus 1 is equal to xk, and then rather than writing delta t d divided by kt by a force, let's call this a drift, right? And then let's put also a Wiener noise, right? So as long as we have these ingredients, we generate basically the same mathematics. And I want to emphasize this because the theory of stochastic processes is used far beyond molecular simulations. Actually, it's probably used more outside of a molecular field simulation regime and field. For instance, for a long time, it was used in understanding financing and stock market oscillations. It's been used to understand even generative models for AI, right? Where you might be familiar with diffusion models, the ones that many generative AI use to generate pictures. The way that these models work is, you might have heard, by introducing noise to the picture and then learning to denoise, right? So basically what they do, now your picture is a coordinate, a pixel in your picture is a coordinate, so it can go from a certain value to another value. And you forget about the drift, you have noise. So you generate a diffusion of the pixel, and by doing this you start from a particular set of, let f be x the set of pixels in your image. By doing many of these steps, you get a completely white noise picture, because it basically is equivalent to start from a configuration and keep on adding Brownian noise until you lost completely the information of the initial state. And then diffusion model train a network to denoise each step. Now I'm cutting over some math. If you're interested, you can follow my course in statistical physics on neural network in the first semester. Probably already graduated by then, but never mind. And the idea is that once you've learned to do this noise and denoise, basically to trace back a diffusion process, to learn it, to sort of trace it back, then you forget about the upper part, you sample white noise, and you generate an image. Right? So you see, the theory of diffusion processes is extremely useful, and it's been applied to a large variety of fields. And I just realized that somebody stole the erasers, so I have to put this on hold. Okay. But going back to the specific case of molecular processes, molecular transitions, we identified as a prototypical example a path like a conformational trajectory associated to, say, allosteric regulation, folding transitions of a protein, or complicated ligand binding processes, protein-protein interaction, anything that has an initial state deconfiguration state, a final state deconfiguration state, or an ensemble of initial states and an ensemble of final states. So, what the main result we achieved yesterday was to express the probability of a path, which I now will write in the following way. I express a probability with square brackets, and I use square brackets because this is a probability that depends on a function now, rather than on a variable. So technically it's a functional. Okay? And the probability of this path is up to some normalization, the exponent of negative the sum over k of xk plus 1 minus xk plus, we call it delta t d kt grad uk squared divided by 4 d delta t. Remember? So that the probability to start from a point x naught and arrive to a final point x after n delta t steps, which I will call t, okay, final time interval, is obtained from this path expression marginalizing over all the intermediate steps, which involves n minus 1 integral over the intermediate positions. Right? So rather than writing explicitly this n minus 1 integral, we chose to borrow the notation from quantum mechanics and write this in terms of a path integral using the quantum mechanical notation. And we reminded ourselves that this sort of resembled the expression for an imaginary time Feynman propagator. Or let's keep the conventional Feynman propagator for the moment, which is the one that solves the Schrödinger equation. This is the Planck's, the Dirac's constant, 0 t q times of m minus u of t. Right. And he emphasizes both the analogies and the differences between the two. First of all, the most striking analogy, of course, is that you have an I while you don't have a I. So while this is strictly speaking the probability of a path, this is a probability of a process, this is an amplitude for a process, and this is a phase associated to the path. It's not even the probability of a path, amplitude for the path, because if you take a square modulus of a pure phase, you get 1. So while this is the amplitude of a process, the phase there cannot simply take in the square modulus of, because then we're going to be trivially 1. So the way you have more probable paths here is by looking at paths that maximize this exponential weight or minimize this action. We identify this as the action over the trajectory q, So we call this the Gonzaga-Mach loop action, remember? So in stochastic processes, the most likely, or what we call the dominant reaction pathways, are those that minimize the Gonzaga-Mach loop action. While in quantum mechanics, the most likely processes are those that extremize this phase. Because basically if you impose delta S equals 0, you get that you slightly perturb your path, the action is stationary to linear variation in the path. That's the condition of gradient over the path, right? So this means that all the path, so if you have a path with delta S equal to 0 and you slightly perturb it, to linear order in the perturbation, the action doesn't change. Which means that the path constructively interfere because the phases are similar, right? Conversely, if you take a wildly different path, the values of the action is so large that basically you get random phases adding up, which basically lead to, on average, destructive interference. So this explains why in quantum mechanics the most likely path in the path integral obey this property. And do you know what this property implies? Stationary action. What does stationary action mean? If you take an action defined as dt q dot square 2 of delta x minus u and you impose stationarity, what do you get? And what equation of motion do you get? No. No. The most probable action, let's do it. Okay, the simplest way to do that is to take S and rewrite it as negative d tau of q negative second derivative with respect to time of q. I have taken by part one of these time derivative here. Right, q dot is q double dot with a negative sign. So that's negative second derivative with respect to time of q. Of course, you keep on having 1/2 mass minus u of q. Now, if you differentiate this object with respect to q, well, you can do this on the right and on the left, so you can do it twice. So basically, when you do it here, you get an acceleration. Right? When you get it here, you get a gradient. So basically, this condition will give you mass times acceleration equal negative gradient of u of q. What is this? Newton's equation. So, path integrals, I'm slightly detouring from my course, but I think it's interesting to build this analogy. Path integrals explain very naturally why this guy doesn't wiggle around space but follows a classical trajectory, right? This is one of the great advantages of path integrals. They express quantum mechanics in terms of classical trajectories, right? But they tell you that you have to sum over infinitely many classical trajectories. Okay, if this was true, why, if I throw a chalk, does it follow a parabola while it is allowed to follow any path? Well, what we have learned is that all the paths except the parabola, which obeys this equation, badly interfere. And so the only paths that really remain are those extremely close to the classical path. They are the only ones that really interfere constructively. That's how classical mechanics emerges out of quantum mechanics. And the dominance of the path bundle around the classical trajectories over all the others is controlled by how fast these oscillations go, which comes with a mass and h bar and blah blah. You see, if h bar becomes very, very, very large, these oscillations are very slow, so you need many, many, many paths, and therefore your quantum mechanical delocalization grows. Conversely, if the h bar is very small, a tiny change in the path will lead to a very large phase oscillations. So only path very, very round, now very, very much focused around the classical trajectories will contribute, right? And therefore, in the h bar equal to 0 limit, you get the classical mechanics out. Okay? I found this, when I first learned about path integrals in quantum mechanics, I was inspired, deeply inspired, because when you learn about quantum mechanics coming from classical mechanics, you get a trauma. Because you learn about Newton's equations and they all make sense. And then you make them even Hamiltonian, they even make even more sense. Everything is nice and symmetric. And then you learn classical electromagnetism. Fine, then you couple particles to fields. Fine, they all make sense. And all of a sudden you talk about, somebody comes in class and tells, forget about trajectories, there's an uncertainty principle. You cannot really talk about that. Here is a beautiful wave function. This is something that is completely different. So it's, how do I approach classical behavior for quantum behavior if I have to completely change mathematical formalism? Now, there is the so-called Ehrenfest theorem that relates the averages of wave function to classical equations of motions. But I found it difficult to grasp that at some point you need to jump from an entirely different mathematical perspective. Now, Feynman path integrals instead do that very much naturally. You rewrite quantum mechanics as a collection of infinitely many classical paths. And then you have a very, very well-founded strategy to identify the paths that dominate, depending on your physical parameters, and this naturally breeds classical mechanics. Okay? So yes, when I walk through the door, I need to go around this wall because all the paths that go through the wall are destructively interfered. And only the path in which I happen to go around happens to have a finite probability. Amplitude, which translates into a finite probability. Okay? And I'm telling you a little bit about quantum mechanics, not because this course is about it, but because we can sort of inherit some of this discussion in here. And we can ask ourselves, what are the most probable pathways for protein folding? And they are those who minimize this. And this is the starting guiding line for a number of approximations you can develop. My personal word line into the molecular field simulation comes from quantum mechanics. And I was working on path integral integrations and methods in quantum field theory and strong interactions. And then I started to be fascinated by the idea of being able to translate these approximations or being inspired by them and put them back into molecular simulation, see whether you can help. And we'll see in a moment that there is a fundamental difference between the formulation in which you think about generating the trajectory with an equation of motion, the stochastic equation of motion that the Ito rule generates, and one in which you compute directly probabilities by evaluating path integral. Let me rephrase this because this is a very important point. So based on everything that we have discussed so far, we have two completely equivalent ways to compute the probability to find the particle at point x at time t. That's our goal. Okay? One way we have discussed so far is start from, okay, this probability in general will depend to some initial condition, which could be, for example, the initial position, but it could be an ensemble of initial positions. It doesn't really matter. You have to convolute over the initial conditions. But let's say the probability of thing being in X at time t given the initial condition, if you have this, you can simply convolute this with the distribution of initial conditions. You have everything, right? So let's say this is our goal. We have two ways of doing this. We start from x naught, and we integrate Ito's equation many times, generating Langevin dynamics, right? We are not very much interested in the path at the moment, since our goal is not to reconstruct at the moment the full path probability. The goal of what that we wrote here is to reconstruct the probability of being in the final position, right? You with me? So what we do, we repeat this many times, and we look at how often, so we say we split space into cells. We repeat the process many, many times, and we count how many times we end up in a cell, in another, right? We build a histogram, right? And at least formally, this histogram, well, it's something you can do in 2D very easily, so to say. You will, by doing this process over and over, this histogram will basically be an approximate estimate of the probability, which becomes exact in the limit of infinite statistics. Okay? What does that mean? It means that any average over the final position evaluated with a histogram will be, by central limit theorem, an approximation of the expectation value over the correct probability. You with me? Now that's strategy number one. Well, in principle, strategy number two is so much more complicated. It says, take all the paths that connect your initial position to any of the paths. So you want the probability in X, evaluate this, including a normalization for all the paths, and this will give you the probability in X, right? So basically, to be specific, what do? You divide your X integral, X range in, now I did it in one dimension since I used this as time, in a number of windows, and then for each window I repeat this calculation. I sample this huge integral with some Monte Carlo method. This is a multidimensional integral, right? So I use Monte Carlo method to sample multidimensional integral. And in principle, I could reconstruct this probability. No? But this makes very little sense from the point of view of computational physics, because it is a damn hard integral to do. Think about doing that by throwing random paths and connecting points and, So what is the advantage from the practical point of view of the computational framework, of the path integral framework? Because you see, if you start from the left side, you generate paths that go anywhere. You start from the initial condition, right? And you generate paths that go everywhere in space. And out of these infinitely many final destinations, I have to throw away everything except the probability in one point, that is the one that I'm interested in. Right? So this is good if you want to compare probability to reach different destinations. Because you have many, many alternative destinations, and you start from an initial condition and you count how many times you end up in any of the destinations. Okay? Now think about a different problem. You're asking now the question, what is the most likely way people go from A to B? Only to B. Now, I'm not interested to ask the question, where do people most often go after 10 steps starting from A? I'm actually asking the question, how do people get from A to B in these steps? So I'll give you immediately two analog questions. If you treat people driving as stochastic processes, which it is true in Rome, it is partially true in Milan, it is very true in Tangier, but it's not true in general. Okay? So it's just an analogy. You may ask the following question. Where are the drivers that are on a given highway station at noon? Where are they at 5 o'clock p.m.? Right? So you condition your system to, you look at all the people that pass the highway station at the same time in Milan at noon, and you ask the probability of where will there be after 6 hours. Now, if you ask Google Maps and probably pay a lot of money, you'll get a distribution of locations of cars. And this is probably interesting for those who run whatever business, okay? Or, add an analogy. Suppose you click on a given website. What is the most likely site that you will visit after n clicks? Right? And then this is all. I don't need to tell you why this is relevant for a business point of view. Okay? Well, this is the way to go. Now, let me get this approach. Suppose you want to ask, how do people get from Rome to Milan in 6 hours? Let's say in 12 hours. 6 hours, there's only one way to go, by car. Let's say in 12 hours, right? So if you ask these in 12 hours, there will be people that will stay in Rome for a little longer, go to see their aunt, have a coffee, then take the highway and go straight to Milan. There will be people that go to to Florence, stop stop for a coffee, and maybe walk around the city and go back to Milan. And there will be people that will go to Milan soon, and then since they're there, they go shopping to Monza, go back to Milan, and they will be in Milan at 6. And so on and so forth. Now you might ask, what are the most likely paths? Well, these most likely paths are those that maximize the probability, therefore minimize the Alexander-Mark group action. You don't need to go to all over the world to look for whatever destination. You already have encoded in your mathematics that you're only interested in processes that go from A and reach B in 2 steps. And once again, in the folding analogy, you might say, I have a fully stretched protein, for instance, and I'm asking, what is the most probable protein folding pathway? There will be probably many. So the equivalence of a classical trajectories is this most likely trajectory path, right? A dominant reaction pathway. When we will discuss the rare event problems, we will see that there is a particular advantage in using this second approach, the one that fixes the boundary conditions. But we will not discuss that now because the lecture is not about real events yet. Okay? But keep in mind that we will go back to these ideas. Later on, we will discuss sampling strategies. But for now, I just want to say, I appreciate that these different approaches, the integration of equation motion and the path integral, are complementary in what they achieve. Number one. They are better suited for different questions, even if they are formally equivalent. Number two, they are ubiquitous in the theory of stochastic processes. Again, a good algorithm that tells you how you click from state A to state B allows you to place a good advertisement in the middle. Okay? And I want to go back to tell you something which now you can appreciate from the classical analogy we started off with at the beginning of this lecture. And it's the following. Remember, we said if h bar is very, very, very large, I have many constructed interference paths. So my alternative trajectories range grows, and that's why I see quantum delocalization. Right? Now see what happens. Conversely, when h bar becomes very small suddenly, all of these paths destructively interfere except those that are very, very narrowly picked around the classical path, aka the classical. Okay, great. Forget about that for the rest of the lecture and look at this path. Instead of looking at the continuum part, look at here. Now, in general, if my time t is long enough, okay, if my time t is long enough, at each step, I will make a displacement that is determined by the eta rule, right? And I can estimate more or less how far I get. This is the typical distance I cover in a given time interval. Now suppose that you ask for probability of getting from x to t in a time interval that is so much shorter than this natural time it would take the system to explore configuration states until you reach that point. You follow me? Let me give you a better visualization of this. Say I'm asking what are the most probable paths that get me from x to y, right? Now, suppose I integrate on the fly the equations of motion and I'm drawing the picture on the board, okay? Every click is a time step. Click, 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 click. I can go on forever. Now, if you allow me for a moment of neglect to force here just to make a calculation easier, you discover that the typical displacement it takes in n steps is, well, in one dimension is 2D, in 3 dimensions there's a 3 here. Okay, it grows linearly with t. So this allows you to estimate more or less how long does it take until you reach a place that is that distant from the initial place, right? It would be something like x minus y. If x minus y is the distance, the time would be of order x minus y divided by 2d. That's more or less the order of magnitude, right? Squared. Okay? Now, suppose you ask the question, what is the probability that I go from x to y in a time t that is much shorter than x minus y squared divided by 2b? Okay? Why should I ask this question? I don't know, maybe because I'm interested in those processes for whatever reason. Early folders that survived the quality control machinery of proteins, or I don't know, whatever stochastic process that outlies all the others by happening much faster. Okay, what is the probability that car that leave Milan at 6 a.m. arrive at Rome at noon, 6 hours later? Now, this is about the minimum time it takes. Guess what? Where do these cars go? They all go through the same route, right? They must go through the A1 or what, A4, I don't remember what is the name. The key highway connecting Milan and Rome, because that's the only way you can go from Milan and Rome in 6 hours, right? By car. Similarly, because of, if you look at the path integral that I just erased, but you have it in your notes, and you're now asking the probability to make it from A and B in a number of steps that is so much shorter than it would be. The only way to do that is to have very large jumps, right? Instead of doing many small jumps, you have to make very large jumps. Correct? E to the negative xk plus 1 minus xk squared divided by 4 dt. Right? This is the weight of a path. If my path in very few steps, wants to connect two points that are very different distance, I cannot allow this to do the Brownian exploration they would naturally be led to, where most of the paths do. I'm forced to look only to those paths that are very unlikely process, where the Brownian exploration goes in one direction, for instance, only. You only move towards the target. And these are very unlikely process, right? Well, unlikely process means low probability, means large actions. So, unlikely processes have large actions, and if you compare to, you perturb this unlikely process by a little bit, you get another large action, right? And the difference between two large actions is a large number. So basically, you're getting back to the situation we encountered in the classical limit of quantum mechanics. If h bar was small, a tiny perturbation of the path would generate a widely different action, right? In units of h bar. So, destructive interference. Here, I'm stretching the Brownian motion, I'm getting very large Zager-Mach actions, because I have to do large jumps. And if I perturb one of these, I get a different large action. The difference between two large actions is large. So basically, when you really stretch the process outside this natural regime, you get the same focusing into one event. Right? So basically, these dominant trajectories will definitely dominate over all the others. Okay? Somehow in analogy with how classical trajectories dominate over all quantum fluctuations. What I want to try to say is that this particular expression teach you a lot if you're ready to start to ask questions to them and to address this math properly. For instance, again, suppose we are very, very interested in protein folding, and we are able to simulate protein folding by molecular dynamic simulation, which is only possible with a one special purpose supercomputer today and for very small proteins. But let's suppose we are in 3 decades from now and the magic happens. Computers have evolved, the algorithm has improved, and we can do protein foldings. Okay. You may say, okay, I'm interested in, say, my protein folding occurs in 1 millisecond time. I simulate 1 millisecond of molecular dynamics, and I collect, on average, every simulation, a folding event. Say I simulate 2 milliseconds to be comfortable, and I collect almost every time a folding event. Okay, it's a Poissonian process, so it has a certain distribution. It's not exactly 100%, but let's say within a few time intervals of 1 millisecond, I'm sure that I will get sufficiently many folding events. But this will be, to a very overwhelming majority, folding events that fall into the peak of the probability of the folding pathway, right? Because I've generated with conventional processes, correct? But suppose you're now interested in the following problem, for whatever biological reason. There are folding events that occur very rapidly. How do they look like? Right? Maybe I'm interested in that because, I don't know, I want to escape the probability of misfolding, or I want to escape some post-translational modification that occurs during folding. We demonstrated recently that phosphorylation can occur co-translationally, and in some cases does occur co-translationally. So maybe, you know, those proteins that don't get phosphorylated are those that fold particularly rapidly so that kinases cannot intercept them and do whatever they want to do post-translational modifications. I'm just putting up some random biological questions where this question maybe arise. So I would be interested in the short time tail of protein folding pathways. You might say, okay, you know, short time, less computational time. I have to simulate for less. No, because if you try to do conventional simulations, you will never see those events, because those events have a very small probability in the path space. You can simulate forever folding event over folding event, and you will always see folding events that sort of last a millisecond. But if you were to able to simulate 1 million folding events, maybe you will detect one folding event that takes maybe 200 microseconds. A huge outlier. Wow, then you would get one sample to gain statistics on your problem. You see? Conversely, if you look at the path integral and you set the initial condition, unfolded, final condition, folded, and you set the time at your taste, now you're looking only at folding processes that take that very time. And now your algorithm, I'm assuming you're able to solve it, will select only those events. So in principle, this provides a way to address specifically this question. Okay? I hope this discussion sort of clarifies the richness of distinguishing between probability in configuration space and path probability. Other questions? Yes.
Is there a way to implement these, or
Is there?
I mean, if there is currently a way to implement these, or is it
To connect or to do it? Yeah. Okay. Yes, there is. To approximately implement this and to exactly implement this. And we will deal with this when we do sampling algorithms. Just to anticipate, an exact way to do this is called transition path sampling, although transition path sampling will likely generate transition paths that have likely time. What we developed in our group is an algorithm to put time as an input, and therefore generate a path given the time you provide. But we will probably discuss this, or you might come to my office for, if I don't have the time to focus. I usually don't do my own research in my course. But we see, maybe there is some time to do. I want to complete the analogy between quantum mechanics and stochastic mechanics, because in quantum mechanics we have computed a propagator, but we know normally when you compute the propagator coming from the Schrödinger equation, right? So you have your Schrödinger equation that tells you how the wave function evolves in time. And then what you do, okay, the evolution of the Schrödinger equation is formally written by applying e to the negative I of h bar h t to the initial wave function. This is basically, this is basically a formal equation at this level, because this evolution operator you have to basically solve the Schrödinger equation to compute, right? And this is basically a solution of that. And this is what the path integral does. Now, in our discussion, we have done sort of the opposite route. We first evaluated the probability to get to x and t starting from y, from an underlying Langevin equation. And now we want to get what is the probability that tells me how this probability changes in time. Okay? Well, there is an asymmetry in this, which is I don't have any microscopic dynamics that naturally breeds the Schrödinger equation as a stochastic process, where here I have Langevin dynamics. That's why I was able to first get the solution, and again get the equation. While in Schrödinger theory, you first start from the Schrödinger equation, and then you look for a solution. You see this? In our case, we could sample this probability, and now we can ask the question, what is the equation for this probability? While in Schrödinger, in quantum mechanics, you must first formulate the Schrödinger equation and look for solutions. Now, in the notes that I have sent you, and I will send you the update, there is all the formal derivation if you want to. I am not giving you all the steps of this derivation, and I'm not asking you the step of this derivation. I'm only gonna sketch it. And whatever I sketch is what I need you to remember. Okay? Okay, so our goal is to derive the equation for the probability density in configuration space. And then step one is the following equation that follows from asking, to noting that the dynamics is Markovian. For any Markovian dynamics, the probability to be in x at time t starting from y is equal to to the probability to go from y to some intermediate point, to some intermediate position, or whatever position z in an intermediate time t prime, and then going from z to x in the remaining time, integrating over the intermediate position for every t prime. Well, let's say for any time between 0 and t, the probability to go from y to x is the probability to go from y to some other position in time t prime, and from that position to x in the remaining time. Why? Because basically, to go from A to B, you got to be somewhere at some intermediate time, right? And this is a strict implication of Markovianity, because you see, what happens from z to x is not influenced by how you got to z. And this is a consequence of Markovianity, right? Very good. So this is a fundamental equation that follows from Markovianity. And it's the key to get the equation for P, because d by dt of P is P of x in time t plus delta t, starting from y, minus P x t starting from y, divided by delta t, right? You see? Well, now, the idea is to write this as the probability of going from y to some point z time t and times the probability to go from z to x in the remaining small time interval delta t, integrating over z. This is this guy here. I'm applying the Chapman-Kolmogorov equation that I wrote before, the Markovian implications, to this particular object. Right? The intermediate time is t minus delta t. I subtract the probability of going from t and divide by delta t. Okay? But now I have an expression for this, which comes from the path integral representation that they gave you. This P of x delta t z is proportional to e to the delta x plus d delta t grad u of x divided by 4 d delta t, and the numerator is squared with a minus sign. Right? It's the bit of Onsager-Markov action that concerns this small step. Divided by k. Let me rewrite this because I was writing lower is difficult. So delta x plus d delta t over kt, gradient of u of x, divided by 4d delta t. Okay? But now I recall that the derivative is the small delta T limit, right? Which in our case we know is take it as small as possible, consistent with the underlying Markovianity and overdamp limit and blah blah blah. But all of a sudden, I can Taylor expand this. I can use Taylor expansion. I can use small delta T limits, right? To evaluate this. Use small delta T approximation. And as you will imagine, some of these terms will cancel. These will cancel with some terms here. You will do manipulations, and you see the manipulations in the notes. I jump to the conclusion. Okay? See if there is anything that I missed. No. Okay. I'm learning to, I'm forgetting how to write since I'm too used to be able to do cut and paste. So it's d Laplacian plus beta grad u of x dot grad plus beta Laplacians of u dot p of x. P. These are differential operators, you see? Differential operators. So this is a partial differential equation, just like a Schrödinger equation. Okay? Well, we see some kind of aspects that resemble the Schrödinger equation. We see the Laplacian there, for instance. Plus, we see a function that multiplies the wave function. In the Schrödinger equation, you have u times psi. Here you have Laplacian of u times psi. Well, let's make the analogy even closer. So instead of writing this way, we write this as a negative. So I'm putting a negative sign everywhere. I write a Fokker-Planck operator, P of xt, and H is negative Laplacians, negative beta grad u grad, negative beta Laplacians of u. D, sorry, D, everywhere. Okay, this equation is called in two ways, depending on what side of the Berlin Wall you used to be. In the West, it was known as the Fokker-Planck equation, after two Germans. I'm not sure whether they were Austrians. Planck was German. I think also Fokker. Anyway, people from the West. And in the East is called the Smoluchowski equation. Smoluchowski was a Polish, if I remember well, mathematician. Fokker-Planck Smoluchowski, if you don't want to be wrong, you will see the spelling S-M-O-L-U-C-H-W, no, C-H-O, forgetting how to write. Smoluchowski, Smoluchowski, I guess. Anyway, it's correctly spelled in the notes, hopefully. The Fokker-Planck equation, we will call it from this point on. But we give credit to Smoluchowski, who actually, I think, discovered it before Fokker-Planck. But sometimes people are unlucky and they don't get Nobel Prizes when they should, for whatever political reasons or historical reasons. Okay, so the Fokker-Planck equation is a fundamental equation of stochastic processes. It doesn't appear only in biophysics, it appears everywhere, blah, 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 blah. You should be extremely worried if you look at this equation. Because you see, when we do quantum mechanics, one of the things that we immediately want is the Hamiltonian to be an Hermitian operator. This has enormous implications. First of all, the eigenvalues are real. You have a complete set of eigenstates. And since the eigenvalues are real, the evolution of the wave function is unitary. Right? Because now the time evolution, remember in quantum mechanics, when you look at the time evolution of wave function, basically what you do, you have a sum over the eigenstates times coefficients, times the corresponding eigenfunctions times some coefficients that depend on the initial condition. Okay? And if these are real, when you take the square modulo of this, you keep on getting the same result. Okay, you get the probabilities are conserved. So in other words, the fact that this is a Hermitian operator enables you to conserve the mass or the number of particles, whatever you want to call it, during dynamics. The probabilities don't just die off and disappear. If the probability were being suppressed with time, the particle would disappear. Right? The fact that a particle doesn't disappear is from the fact that when you take the square modulo of this and you have real eigenvalues, you get unitary evolution. But to get real eigenvalues and unitary evolution, you need an Hermitian Hamiltonian. Yes? Remember this? Well, I think you should be clear, it should immediately be clear to you that this is by no means an Hermitian operator. Why? Well, let's look at it. It's a linear, so the Fokker-Planck equation is a linear equation. So if each individual term is Hermitian, the operator is Hermitian, right? So the first one is the kinetic energy operator, after all, right? Of course, it has a diffusion not 1 over h bar square over 2m, but if you call h bar square over 2m equal d, you get a kinetic energy operator. And that is well behaved. Right? This term here is a multiplicative term. You might call this v of x, and then you have a potential operator, right? And it's a real potential operator. It can be as well behaved as you want. So that is also under control. But problems arise from here. And specifically because we have a single derivative operator here. In fact, how do I know that the single derivative operator is not Hermitian. So let's take one little digression. Let's look at the gradient operator. Okay? Okay? What does Hermitian mean? Do you remember? We construct the adjoint operator. And it's Hermitian if it's self-adjoint. Okay? So, let's build two test functions. I'm using the same inner product as quantum mechanics, by the way. Well, no, not getting the complex conjugate because everything is real here. So I get an integral dx phi of x gradient psi of x. Okay? Now, the adjoint operator is the one such that this will give me this, right? So d dagger, if you want, is the operator for which d dagger psi phi times psi is equal to phi d psi. Okay? And it's clear what it is. I integrate by part, and this is negative dx gradient of phi times psi. So d dagger is negative gradient. Integration by part. Bringing the derivative on this side gives me the negative sign. So this is equal to this. Well, I'm ignoring boundary terms because the function will behave at infinity, blah, 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 which means that the dagger operator is the negative of the gradient. So this is spoiling hermeticity. By the way, in quantum mechanics, we don't have this problem with momenta. That's why when we do momenta here, we put an I here. Remember? Because when we do momenta, we put an I, and we go to the other side. I get the negative side, but I also get the I takes care of it, basically. And therefore, I get there is Hermitian. So momentum is an observer. Okay? So the question is, how can probability be conserved if the fundamental operator of Fokker-Planck dynamics is not Hermitian? Because we learned before that, at least for quantum mechanics, hermeticity was a very, very fundamental property that I wanted. Well, I had also the square modulus, which we don't have here. So, but the question is, if I have a non-Hermitian operator, I don't have real eigenvalues, I don't have a set of, my spectral properties go bananas. And all the nice properties of operators are lost. It turns out that the Fokker-Planck operator is a very, very gentle kind of non-Hermitian operator, as we shall see. A kind of non-Hermitian operator, which we will explore, the spectral properties of which we will explore, which has, I anticipate, two fundamental properties that normal non-Hermitian operators don't have. Number one, and I will show it now, it conserves probabilities. Number two, it has a well-defined real spectrum bounded from 0 up. So the lowest eigenvalue is going to be 0, the first one is going to be positive, and blah, blah, blah. Okay? I'm going to write these things up. But what I want to say is that normally non-Hermitian operators don't have these properties. But this is a very, very lucky Hermitian operator. And it should be because it follows from a dynamics, the Langevin dynamics, which conserves probability, right? Particles go somewhere. They don't disappear in Langevin processes. So the underlying dynamics conserve probability. So it generates a partial differential equation that, even if not Hermitian, reflects this. So the non-Hermiticity reflects the time irreversibility. but it does it in a way that preserves probability and real spectrum. Today, I will not prove all the spectral properties of the Fokker-Planck equation. We will deal with it next lecture, and they are very important for building algorithms to do data analysis, for instance. But I will convince you that the Fokker-Planck equation conserves probability. Okay, to prove that the Fokker-Planck equation conserves or preserves the total probability, the normalization, or which means basically that don't create or annihilate particles. Okay? So it's equivalent number of particles, mass. All these things are equivalent if you're not in the relativistic quantum mechanic regime, or in a relativistic regime in general, where you can change the mass by going faster, for instance, or you can generate kinetic energy by reducing the mass of an object, like in fission. The mass of the products is less than the mass of the other nucleus, and that's why the remaining energy has to go in kinetic energy. These are all phenomena that we are not concerned with here. Okay? So the idea is this. Let's define an object called minus d grad p plus beta grad u p. It's my definition. Gradient of p, gradient of u times p. So this is a 3-dimensional vector, right? Because the gradient has 3 components. Yes? So it's a vector, we call it a current. It's a probability current, Fokker-Planck current. Why probability? Because it's built out of a probability. Okay? Now, it takes you basically 5 seconds to realize that the Fokker-Planck equation can be equivalently written in the following way. dt of p equals negative gradient of j. Look, take a divergence here. Sorry, divergence of j, not negative. J is a vector, this is divergence. If you take a divergence, you get Laplacian, and then the divergence will act here, and you'll generate the other 2 terms of the Fokker-Planck equation. But what kind of equation is this? Continuity equation, right? Equazione di continuità, continuity equation. And normally when things are, the integral is conserved, right? Well, you can think about this. We know a similar equation for the electric field, right? It's called the first Maxwell equation, which tells you basically you can use Gauss' law. You sum whatever charges in it and the flux of this, and they must be equivalent. Because the integral of the flux, the surface integrals, well, you get the integral divergence, and you can use, from here you can get Gauss' law. You use the flux of the electric field is equal to the integral of the charge contained inside, right? Gauss theorem. Remember that? Well, if you can use it here, you can use it here, right? And what is it telling you? That if you have a certain probability focused inside a region, and you can build a surface around it, a Gauss surface, you can only escape from this region by a current that goes outside. So in other words, the total mass is conserved. Let me give you a demonstration. No, the demonstration. This doesn't need demonstration. It's already demonstrated. It says that I just wrote the Fokker-Planck equation in a different way, but let me give you a visualization. Say we have something like this. And we put some distribution here. So we put 10,000 particles all in a point. This is the potential. And we let them evolve according to Langevin equation. Well, then we'll start doing Brownian motion, but overall, well, at very short time it will be a Brownian motion because at very short time you're dominated by the noise. You have a little bit of a correction from the drift, right? Force, and the drift will be asymmetric. So after a little time, the distribution will be this, and after some longer time will be probably this, and if you wait long enough, it will be here with the proper normalization. Now, if you take any finite distance, any finite segment, you'll discover that the amount of probability that decreases here is due to the flux of the current through this point. So the probability doesn't go anywhere, it fluxes away. It flows away, sorry. Okay? So yes, at least we know that the Fokker-Planck equation doesn't screw up the number of equation. But now I finally am, in the remaining 5 minutes of this lecture, able to close an important open loophole we had long ago. Remember, at some point I derived for you the fluctuation dissipation theorem, which relates the time correlation of the noise to a quantity that contains temperature, mass, and gamma. Now, depends which version you're using. This is for the overdamped. The underdamped has a slightly different term here because you remember they are related by a scaling, by m gamma. So this is for the overdamped. And I told you one thing. I told you this particular relationship is there because in order to allow for the first principle of thermodynamics, you want the energy that you lose with interaction with the environment, which in that model were the harmonic oscillators, to be compensated by the energy you gain from the interaction with the environment. And if your initial condition, your environment was at a temperature T, this was set in a nice, fine, detailed balance from energy loss and energy gain that ultimately settles for evolution, for equilibration. I didn't prove that to you. I only said that to you. I didn't prove that because of this result, you will get to the Boltzmann equation. I just proved to you that it's there to ensure that this happens, which is true, because if you screw this relationship, the result that I'm going to tell you is not going to work. Because this relationship was used to derive the expression for the probability, right? And the expression for the probability was used to derive the Fokker-Planck equation. So if you choose a different value there, you get a different Fokker-Planck equation, right? Now I want to show you that the Gibbs measure solves the Fokker-Planck equation. Okay, so let's take P not t, I take a function that doesn't depend on t. And I call it equilibrium because it doesn't depend on t, stationary if you want. And I call it one constant, which I will fix later, and the Gibbs distribution, beta u of x. Well, the constant is obviously the Cartesian function to the minus 1, so let's write it already. This is a function. I define it for you. I haven't derived it here. We derived it from maximum entropy principle, if you remember. But let's forget about it. I'm giving you this function. So let's compute the current associated to this function. Right? Well, it's negative d, the gradient of this function, which is negative b gradient of u p of x, right? Plus beta gradient of u, this function, p of x. I apply the definition of current right there. Here. What is this? How much does it make? What is this? How much is this current? Compute this. Negative grad UP plus gradient B dup equal? It's my handwriting that is probably too much for that. Huh? Negative gradient of u times p plus gradient of u times p equals? 0. So no current. And of course the time derivative of t is equal to 0 because there's no t. So this is a distribution that solves the Fokker-Planck equation and doesn't have any current. It's the stationary distribution. Once you reach the distribution, no current flows anymore in your system, and you're stuck to that distribution forever. So yes, we have demonstrated that the Langevin dynamics eventually samples the Boltzmann distribution for long enough trajectories because the associated Fokker-Planck equation has the Boltzmann distribution, or Gibbs distribution in this case, as a stationary solution. Could there be alternative stationary solutions? Maybe there are two stationary solutions, the Boltzmann equation, the Boltzmann distribution, and another one. The answer is no, for reasons that will become clear in a moment, not today. But we will show that we will map basically this into quantum mechanical problems with a real nice and behaved Hamiltonian, and the Hamiltonian is only one ground state in classical, in finite dimensional systems. So for any finite dimensional system, there is only one ground state, which means there is only one stationary solution. So yes, the Fokker-Planck equation defines a stochastic process that has all the nice properties that we want. It comes from the Langevin equation. It has a solution in terms of path integrals. The solution in terms of path integrals offers complementary information with respect to the direct integration of the equation of motion. We discussed the direct integration of the equation of motion is good to get to the bulk of the probability of processes, but the path integrals allow you to play with the parameters and go and hunt for corners of the probability that would be very difficult to sample otherwise. So, and there are other very important properties that we will discuss when time will come. So, path integrals are useful, and we derive the associated Fokker-Planck equation. We discovered that it's basically a Gauss. You can use Gauss equation to relate. You can write it as a continuity equation by a Gauss law that concerns probability. What remains open is the fact that it's non-emission, which might lead to, I don't have a basis of eigenstates and eigenvalues that is orthonormal, so which you might say, who cares? But spectral decompositions are very useful, as we will see. We will have to understand what is the physical meaning of the eigenvalues of the Fokker-Planck equation? Now, for the Hamiltonian, we know it's the energy. What is this for the Fokker-Planck equation? But this is the tale for another lecture, okay? Thursday's lecture. A posto. Thank you.